This is a pre-built version of the application. So if we go ahead and run the server and two clients, and this will be the server, and this is the first client, and this the second client. And here we are running in ASCII mode, which makes it easier for testing, and later on I will run it in regular mode. So Alice uses this number as P, and this number as alpha, and this one as the private key D, and she calculates beta and sends P, alpha and beta to Bob, and Bob receives those P, alpha and beta, and he will be using this as his P, and this one as his primitive element alpha, and this number as his private key D. So he calculates beta and sends his P, alpha and beta to Alice. And she will try to send this ASCII message, and she will choose this ephemeral key, and let's first try to sign the message with a made up key. See what happens. So she calculates R and S, the signature parameters, and sends the message X with calculated R and S to Bob, and he receives those and calculates T. So he calculates this, so T congruent to beta to the power of R multiplied by R to the power of S, all of that mode P. And he also calculates alpha to the power of X in mode P, and he determines that T is not congruent to alpha to the power of X in mode P, which means that the message was not signed with Alice's private key. So let's do the same thing, except now sign it with her private key. So we'll use the same ephemeral key, and her private key D is this number, so she does the same thing. She calculates R and S and sends X and R and S, the message with the parameters, to Bob, and he receives those and calculates T and alpha to the power of X, and they're both the same. So T is congruent to alpha to the power of X in mode P, which means that we have a valid signature. and Eve can see Alice's P, alpha and beta, and Bob's P, alpha and beta, and she can see both messages that were sent from Alice to Bob. But in order to sign those messages as being Alice, she needs to solve two discrete logarithm problems. Then she can use D and the ephemeral key to sign the messages this way. So S is congruent to X minus D multiplied by R, all of that multiplied by the inverse of the ephemeral key in mode P minus 1. Now, before proceeding with the code, let's do a quick summary and also a proof. So, Alice wants to send signed messages to Bob. So she starts by selecting a large prime number P, and then picking a generator alpha in ZP star or a subgroup of that, and then she picks a private key D from 2 to P minus 2, and she calculates the public key beta, which is alpha to the power of T in mode P, and she sends P, alpha and beta to Bob. And then she picks, for each message, she picks an ephemeral key from 0 to P minus 2, such that the greatest common divisor of the ephemeral key and P minus 1 is 1. And then she calculates the signature params for that message, so R and S, and R is congruent to alpha to the power of the ephemeral key in mode P, and S is congruent to X, the message, minus D multiplied by R multiplied by the inverse of the ephemeral key in mode P minus 1, and she sends X and the parameters R and S to Bob. And in order to validate that the message was signed by Alice, Bob calculates this, so beta to the power of R multiplied by R to the power of S. He validates if it's congruent to alpha to the power of X in mode P, and if so, then we have a valid signature, otherwise we have an invalid signature. So what we want to prove is that starting from here, alpha to the power of X congruent to beta to the power of R multiplied by R to the power of S in mode P. So if we start from here, we can end up in here. In S is congruent to X minus D times R multiplied by the inverse of the ephemeral key in mode P minus 1. So we replace beta by alpha to the power of D. So we end up with alpha to the power of D to the power of R, and we replace R by alpha to the power of the ephemeral key. So we end up with alpha to the power of the ephemeral key to the power of S, all of that in mode P. So we get this alpha to the power of D times R multiplied by alpha to the power of the ephemeral key times S, all of that in mode P. And alpha to the power of D times R plus the ephemeral key times S in mode P. And from Fermat little theorem, we have this A to the power of M is congruent to A to the power of M mode P minus 1, all of that in mode P. So we use 1 and 2. This gives us that X is congruent to D times R plus the ephemeral key times S in mode P minus 1. And if we rearrange, we end up with S is congruent to X minus D times R multiplied by the inverse of the ephemeral key in mode P minus 1. So this. I will start by creating a new project. And we will need this jar file to do JSON. So we will go to properties and Java build path, and we will have two packages, one for the server side and another one for the client side. And on the server side we will have two classes, a server class with a main method and a server thread class. And on the client side we will also have two classes, a client class with a main method and a client thread class. And both the client thread and the server thread classes will extend from thread. And we will start with the server side, and here we will have those three instance variables, a server and a buffered reader and a print writer, and we will initialize those in the constructor, which takes in a socket and a server instance, and it uses the socket to initialize the buffered reader and the print writer. And this method does message forwarding, so it uses this print writer to do that. And the server will be listening on this port, and it has two instance variables, a server socket and a set of server threads for handling communications between this server and the different clients that it is interacting with. And we will have this get method for the set, and this method does the message forwarding from Alice to Bob or the other way around. So it uses the forward message method on the server thread. And in main we will instantiate a server instance and a server socket instance, passing in this port number. And Eve indicates that she can see all communications, and when a connection comes in from a client we accept it. We use the server socket to accept it, and we have a server thread that will handle communications with that client. And we add that server thread instance to the set of server threads, and then we call the start method, which will end up triggering a call to this run method when the operating system decides to do so. And here Eve indicates that she can see P, alpha, and beta for Alice or Bob. And if we have a signed message, then she indicates that in order to change the message and sign it again, she needs to solve two discrete logarithm problems and obtain D and the ephemeral key. So she would obtain D by solving this discrete logarithm problem, log base alpha of beta in mode P, and she would obtain the ephemeral key by solving this discrete logarithm problem, log base alpha of R in mode P. So this should do it for the server side. And here we will keep track of this client name and P and alpha and the private key D and the public key beta and the other party name and P and alpha and beta. And this flag indicates if we are running in ASCII mode, and this one indicates if we are ready to send and receive messages. And we have get and set methods for those, and this one turns character to ASCII and this ASCII to character, and this one checks if two numbers are relatively prime. And the client thread keeps track of those two instance variables, the buffered reader and the client, and they are initialized in the constructor, which takes in a socket and a client instance and uses the socket to initialize the buffered reader. And this method handles the setup phase, so it prompts the user to enter the name and P, which is a prime number, and a primitive element alpha, and a private key D chosen from this set from 2 to P minus 2, and it picks up those values and calculates public key beta and puts everything in a JSON object so the name and P and alpha and beta, and sends it to the other client. And we will have this method for signing and sending messages, and this one handles the communication. So it initially calls the handle setup phase, and when this happens, we break out of this always true loop, and we go into this other always true loop, and here we can sign and send messages, and we call this communicate method from here. So here we indicate if we are running in ASCII mode, and the server will be running on localhost for the purpose of this tutorial, and on this port number. And we instantiate a client thread for handling incoming messages, and we call the start method on it, which will end up triggering a call to this run method when the operating system decides to do so, and we call the communicate method, passing in this buffered reader. And this method handles the sending of signed messages. So it takes in a message and R and S, and packages those in a JSON object and sends them. And this method calculates the signature params, so it takes in the message and a buffered reader and the ephemeral key, and it prompts the user to enter the private key to sign the message with, and it calculates the signature params R and S, and calls this method to send the signed message. And this method ends up calling the calculate signature params to sign and send messages. So this handles if we are not running in ASCII mode, so we call this static method, character to ASCII. And here we prompt the user for the ephemeral key, and we check if it is relatively prime with P minus 1, and I think this should do it for this class. And this method handles verification of signature, so it takes in X and T, the message, and T, and this is the value for T, and it calculates alpha to the power of X in mode P, And if t is equal to alpha to the power of x, then we have a valid signature, and otherwise we have an invalid signature. And this method handles the receiving of the message and calculates t and calls this verify signature method, passing in x and t. And this is the code that receives the JSON object and determines if it contains the message or if it contains a public key. So here we set the name and p and alpha and beta for the other party, and here we end up calling the receive message method. So this should do it for this class. And finally, let's go ahead and test run the application. So we will have a server and two clients. And this will be the server, and this is the first client, and this the second one. And Alice will have this value for p, and this one for the primitive element alpha, and this one for the private key d. And she calculates the public key beta and sends p, alpha, and beta to Bob, and he receives those, and he in turn will use this value for his p, and this one for his primitive element alpha, and this for his private key d. And he calculates his beta and sends his p, alpha, and beta to Alice. And let's say Alice wants to send this message, and she picks this ephemeral key, and let's go with a made up key for now and see what happens. So she signs the message with that made up key and calculates signature parameters R and S, and sends the message with R and S to Bob, and he receives those, and calculates T, and calculates alpha to the power of x, and compares it to T, and determines that T is not congruent to alpha to the power of x in mode P. So the message was not signed with Alice's private key. So let's do it again, and this time let's use the same ephemeral key, but use the private key for Alice this time. So she does the same thing. She calculates the signature params R and S and sends a message with those params to Bob, and he receives those and calculates T and alpha to the power of X in mode P, and they're both the same. So he determines that we have a valid signature. So this message originated from Alice. And if he wants to send this message with this ephemeral key, and let's have him sign it with his private key. So Alice receives that message and calculates T and alpha to the power of X, and they're both the same. So she determines that we have a valid signature, and the message originated from Bob. And she sends the same message with the same ephemeral key, but with a made up private key. Then Alice would determine that the message was not signed with Bob's private